Hello and welcome to this chat on Venus. We're going to be looking at Venus, which is the terrestrial planet that resembles the Earth in many different ways, even though it's probably the least hospitable of any of the planets. It's probably the last place that humans will ever step foot in our solar system. Venus, in fact, has so many similarities to the Earth that oftentimes it's referred to as our twin. Of course, we'll see what also went wrong with Venus. At one time, it's thought that Venus was very much like the Earth, but due to the thick atmosphere, greenhouse gases cause it to overheat. So, again, we'll talk about its orbit, its atmosphere, the similar geological features that it has to the Earth, what's different, talk about its interior, and finally, go over some of the missions that we've had to Venus so far. So let's take a look at Venus in terms of its general properties. It is the second closest planet to the Sun, similar in size and composition to the Earth. And as I said, it has a very dense atmosphere with an extreme greenhouse effect. Venus rotates very slowly, and that's a little bit of a mystery why that's so. Its surface is highly volcanic, and it really only has a little bit of water vapor in the atmosphere. Most of the water vapor or water that it had at one time has been destroyed. In terms of comparing, Venus's radius is almost the same as the Earth. It's about 5% off, giving it a slightly smaller volume. And it has about 2.5 times the radius of Mercury for comparison, about 1.8 times the radius of Mars, so it's almost twice as large in diameter. And of course, 3.5 times the radius of the Moon. In comparing Venus to the other planets, we saw earlier when we talked about Mercury, Mercury has very little mass compared to the other terrestrial planets. Even Mars is small compared to Venus and Earth. Venus and Earth are very comparable. Their masses are only off by about 15%. I'm sorry, well, between 15 and 20%. Their density is similar. Venus is a bit lower in density because it doesn't have as large of a metal core. Now, in terms of its orbital properties, its orbit's fairly round. Much like the Earth, it's very low eccentricity. But unlike the Earth, it rotates very slowly, as we said earlier on. Now, it's 0.72 astronomical units from the Sun, so it's a little more than 2/3 from the Sun compared to our own orbit. That gives us about twice as much solar intensity at the location of Venus as we have at Earth. Again, the orbital inclination is not very large. Basically, it's only about 3.86 degrees, which is much, much less than what we saw for Mercury. And strangely, Venus has a retrograde spin. It's the only planet that actually spins backwards. And even more bizarre about it is every time it approaches the Earth, it basically shows the same face toward us. So there doesn't appear to be any true gravitational resonance with respect to the Sun. But there may be a bizarre resonance between the Earth and the Sun and Venus. We're not quite sure if that's just a coincidence or whether that's really true. But again, Venus spins very slowly. We don't know why it has stopped spinning. Some theories have the fact that its atmosphere is so incredibly thick that the friction over billions of years has actually created this slowing. And again, the resonance with respect to Earth, again, we don't know if that's chance or whether that's due to a tidal interaction of some sort. So in any case, Venus's orbit, nothing too bizarre about that. Again, at 2/3 the distance, it gets about twice as much solar intensity as we do, and that's obviously the reason why the atmosphere got so hot. So let's talk about the atmosphere. That's a typo, by the way. Venus does have a very significant atmosphere. In fact, the atmosphere of Venus is the densest of all terrestrial atmospheres. It's 100 times denser than the next densest atmosphere, which we find on the Earth. Now, the atmosphere produces a very intense greenhouse effect where, although very little light makes it to the surface, the small amount of light that does make it to the surface, almost all of it's turned into heat, and that infrared radiation is blocked so it can't escape into space. So Venus's atmosphere, again, very different from Earth's. 90 times the pressure, 100 times the density, and most visible light, again, is reflected by the top clouds. And these clouds are made of a nasty combination of sulfuric acid and haze. But again, the small amount of light that does make it through to the surface is pretty much blocked from escaping because of the large concentration of carbon dioxide in the atmosphere. And again, we look at the atmosphere of Venus and we can understand where the greenhouse effect comes from. 96.5% carbon dioxide. That means that carbon dioxide is a great greenhouse gas in terms of blocking infrared light. Energy comes in the form of visible light from the sun, but it can't leave, as it would normally do for a planet, through the emission of infrared light. So, very, very little of the energy that comes in is allowed to escape, or at least can escape rapidly. It has about a 3.5% nitrogen concentration, but honestly, if we took all the carbon dioxide away, the atmosphere would be similar to the Earth's atmosphere, a little higher in pressure, but our atmosphere is about 80% nitrogen. So if we could somehow remove the carbon dioxide, we'd end up with something that's very similar to the Earth, and at one time it was probably nearly identical to the Earth. The trace gases, again, are kind of nasty. Sulfur dioxide forms with the water vapor to create sulfuric acid. There's also some argon, which is also present in our own atmosphere. Carbon monoxide, which we know is a very potent poison to us. And then a little bit of noble gases, helium and neon. Now, the surface temperature is so hot, 740 degrees Kelvin. It's hot enough to melt tin, and in some places hot enough to melt lead. This is an infrared photograph of Venus, and it shows basically how the clouds are able to prevent infrared light from escaping. Where the clouds are the thickest, you get almost no infrared light. The thinner regions of the cloud deck are brighter because you get more infrared light escaping. But again, the surface is so hot that, it really doesn't, it would make it impossible for humans to exist without extreme protection, and certainly life is out of the question. Again, we look at the terrestrial planets. The greenhouse effect is most potent on Venus. It's second most potent on the Earth, and then third on Mars, and then, of course, Mercury doesn't have an atmosphere to create a greenhouse effect. Strangely, because Venus rotates very slowly, it doesn't have the different convection cells that the Earth has. It basically has a northern convection cell and a southern convection cell. Also, the wind, at least at the upper level, has very, very high velocities. And basically this is because the daytime side very efficiently transfers heat to the nighttime side to keep everything at the same temperature. So Venus takes almost one complete revolution for the surface to rotate once. That means once every 2/3 of a year, the planet will basically rotate. But the wind is moving so quickly, the upper region will be able to circle around the planet in as little as 4 days. And again, this is the high efficiency transfer of heat from the daytime side to the nighttime side.
So again, when we look at the wind flow on Venus, it's fairly unique. Near the surface, there's hardly any wind at all. But in the upper part of the atmosphere, where the pressure is pretty much the same as the pressure here on the Earth's surface, we get a very intense transfer of energy. Now, Venus's atmosphere has not always been an intense greenhouse. At one time, the primitive Venusian atmosphere was very similar to the primitive Earth atmosphere. Now, when the solar system first formed, there was tons of volatiles available throughout the solar system. But Venus, like any terrestrial planet, was too small to retain the most common gases, those being hydrogen and helium, the gases that the giant planets accreted and kept. So all of Venus's atmosphere really came from outgassing, from volcanoes, from impacts. And as this outgassing took place, hydrogen, ammonia, methane, carbon dioxide, and water vapor, all the materials that were trapped within the planetesimals that kept hitting the surface of Venus would basically boil off into the surrounding region. So basically what we had when Venus first formed was this envelope of gas where, again, hydrogen and helium, because they would have very high velocities, would be quickly lost into space. What stuck around were, again, the heavier gases. Ammonia, for instance, is a very common volatile that you'd find in the early solar system. And basically, ammonia would have been processed or would have reacted to the sunlight. So basically, the ammonia would have been broken down into other things, such as hydrogen gas that would have escaped into space like the other hydrogen. But it also would have broken down into nitrogen, and we see nitrogen in Venus's atmosphere today. Methane's another gas that was very common in the early solar system. But like ammonia, it's really not stable in the presence of the ultraviolet light from the sun. So with respect to the methane, methane is easily broken apart by ultraviolet light. It would have been changed into water and carbon dioxide. And of course, water is a very common material throughout the solar system even today, and was very common during the early formation of the solar system. So at one time, Venus had a lot more water than it had today. The water vapor would have accumulated in the atmosphere just like it did on the Earth. As the water reached higher altitudes, it would cool, it would release its latent heat, and produce a thick cover of clouds. Now, eventually, the atmosphere would become saturated. Again, we would have seen this both on Venus, and we would have seen this on the Earth, too. The question is, did Venus get hot very quickly, preventing from the water precipitating and raining down, and therefore forming oceans? And although we really have no evidence of oceans on the surface, any of that evidence has been destroyed by volcanic activity. It's pretty safe to assume that at one time, at least some of the lower basins would have filled with water, producing large lakes, seas, or even oceans. So this picture that we have of early Venus might have been, very similar to what the early Earth was like. In terms of where the oceans blew, it's really hard to know if that would have been the case. The early oceans probably would have had more of a green tinge to them because of the high iron content. That iron wasn't removed until the Earth's atmosphere gained oxygen, so maybe this is not a realistic picture of Venus. But again, we might have had a Venus a long time ago with huge oceans, just like the Earth. Now, if the water condensed to form large bodies of water, like the oceans, it would have been possible for carbon dioxide in the primitive early atmosphere to actually dissolve into the oceans and basically be removed from the atmosphere. And again, this would have made Venus very similar to the Earth during its early history. There might have been even the possibility for life. The problem is, once the atmosphere begins to overheat, there's no turning back. All these processes that led Venus to become more like the Earth would have been reversed rather quickly. So basically, when the Venus formed, it formed when the sun was about 25% dimmer than it is today. So even at that time, Venus was getting significantly more energy from the sun than the Earth even gets today. So it would have been very difficult for it to maintain a stable climate. Now, as the sun got older, its intensity increased. So basically, any liquid on the surface of Venus would have been vaporized as temperatures went up. Surface temperatures would climb, more and more water would evaporate, and this would have created a positive feedback because water vapor is a greenhouse gas. The liquid water would have disappeared off the surface of Venus probably pretty quickly, anywhere from about 600 million years after Venus first formed to about 2 billion years. But it's more likely that it disappeared faster than slower. Now, at this point, Venus is still not the hell that it is today. Even after the water had boiled off the surface, Venus still might have been able to maintain a more reasonable temperature. The problem is, once all the water from the surface is up in the atmosphere, unlike the Earth, which has a nice magnetic field to protect our atmosphere from radiation, and an ozone layer to protect the water vapor in the troposphere from ultraviolet light, Venus wouldn't have had any of that. If it had generated an ozone layer, that would have been destroyed by the water vapor itself. Once the ozone layer is gone and the ultraviolet light can make it down, ultraviolet light would break water down. It would have broken it down into hydrogen, which would have escaped into space, and oxygen, which would have quickly reacted with surface materials. So eventually, even the water disappears, and all that's left is carbon dioxide. Remember, a lot of the carbon dioxide would have dissolved into the oceans if that were the case. Well, the problem is that carbon dioxide would have been released as the carbonates were released during volcanic eruptions. And essentially, we would get to the current point where most of the water is gone, lost mainly to space, and the atmosphere has been replaced by this thick blanket of carbon dioxide, which is essentially a super greenhouse. Now, the question I always get is, would it ever be possible to turn back time for Venus? You know, that's with the assumption that at one time it was much cooler than it is today. Would it be possible to make Venus like the Earth? Well, this process that we call terraforming is really beyond the technology and resources that we have today. We could terraform Venus in theory, but it would probably be more difficult to terraform Venus than Mars or the Moon. And the problem is, first of all, we've got to reduce the number one problem that gave Venus a runaway greenhouse effect in the first place, and that's the solar flux, the energy coming from the sun. Now, you could build sunshades to do that, but you'd need a sunshade probably 4 times bigger than Venus, and that would just require too much energy and too many resources. You'd also have to remove, besides the high intensity of light, a lot of the carbon dioxide from the atmosphere. And finally, somehow you'd have to bring the water back. Again, we could reduce the solar flux using these large
sun shields at what's known as a Lagrangian point, but again, that would really be quite difficult. How do we remove the carbon dioxide? Well, getting rid of the carbon dioxide, if you can lower the temperatures, is not as much of a problem. If you can cool the planet to the point where the carbon dioxide freezes, you could bury it. Or if you could create oceans, you could also dissolve the carbon dioxides in the oceans. But that means restoring the water. And the Earth currently has about 1.35 times 10 to the 21 kilograms of water. You'd have to basically move something as large as Saturn's moon Tethys to restore the water that's been lost. So terraforming Venus, it's possible. It would require a technology much more advanced than what we have today. But basically, the question is, why would you want to do that? Even if you had the energy and the resources, terraforming Venus would require more energy than you would need to create large space colonies in other locations of the solar system. Basically, for the same amount of energy you needed to terraform the planet, you could create artificial habitats to house many more people. So at this point, the concept is a nice thought experiment, but it's really beyond the technology that we have today. So let's take a look inside Venus. Basically, there's no hope for the atmosphere. Sorry about that. The atmosphere is really hot. It's very dense. And really, the sun is getting brighter and brighter as time goes by. Not over our lifetimes, it's not really, but over, millions and billions of years, the sun will only get brighter and brighter, and that's just going to make the greenhouse problem, more difficult to solve on Venus. So the atmosphere is hopeless. What about the interior? Well, here's where Venus is very much like the Earth. The interior of Venus has a basic structure that we see with all the terrestrial planets. A metal core at the center, a dense rocky mantle surrounding the core, and finally a thin crust over the mantle. Now, the core of Venus is probably like the core of both Mercury and the Earth. It definitely has a solid core, but the question is there an outer core which is liquid, like we suspect on Mercury and we know we have on Earth? The problem is Venus doesn't have a magnetic field. If it did have a magnetic field, we'd know for sure that part of the interior has to be liquid. That's the only mechanism that we have so far that can produce, a fairly good magnetic field. However, you also need a rotating planet, and Venus doesn't rotate fast enough to generate a field. So whether or not the part of the core is liquid, we really can't say at this point. There are some measurements that do confirm that the outer core is molten, but again, we don't have concrete data on that. Now again, Venus, like the Earth, was basically heated initially by gravitational energy of things falling inward and giving up their energy. But like the Earth today, most of the heat is being generated by radioactive decay. Now, the mantle of Venus should be very similar to the mantle of the Earth. We would expect iron, magnesium, silicate rock, also probably some spinel, maybe some garnet, and very close to the core, iron, magnesium perovskites. Just real dense, dark rock. We also would expect that the core, having more energy, should generate heat on the lower mantle, and through convection cause these large plumes of hot material to rise to the surface.
This is what we think is responsible on Earth for things like the supervolcanoes that we see at Yellowstone National Park and other places on our own planet. The problem with Venus is there's no plate tectonics. The surface is basically being shaped by volcanic activity and volcanic activity only. And about 500 million years ago, Venus went through this massive episode of volcanism. And we think that the mantle may go through periodic episodes where it heats up from the core. As heat builds, lowers the viscosity, increases convection. We have a large episode of volcanism. And then after giving up its heat, the mantle cools again, becomes more viscous and shuts down the plumes. So after the plume outbreak, we would expect long periods of quieter volcanic activity. On the surface, we definitely see volcanic activity all over the place. There are very few impact craters. Most of the craters that we see are really caldera from volcanic eruptions, and they're all over the place. Now, we have been able to make it to the surface. The former Soviet Union did land a few probes, and when they reached the surface, they saw very dark rock, which is exactly what we expect, from a volcanic planet. We expect lots of this heavy basalt rock, which is common on Earth, especially in places like Hawaii. The surface rock, again, is the result of volcanic activity, lava being given off again and again. And in terms of the range of samples that the landers were able to detect, they detected very dark, dense silicate rock, where the silica levels were about 55%. Well, that sounds high. That is sort of analogous to what we see on Earth in terms of on our own seafloor, again in Hawaii. The surface rock on Venus is very much like the ocean crust that we see on Earth. It's primarily made out of basalt and what geologists like to call mafic rock. In terms of continental crust on Earth, it has a much higher silicate content. Our continental crust, contains granite and in denser places, intermediate rocks like andesite. So, the landers were only able to go into the lower areas where we'd expect the basalt. Would we expect lighter continental rock like we see on Earth? Well, probably not. Even the higher areas, you probably have lighter rock, maybe not quite basalt. But, certainly because Venus doesn't have the plate tectonics that we have, where it was able to differentiate very light continental crust from the darker oceanic crust. We would expect, much denser rock throughout the surface. And again, here's sort of the reverse. Geologically, we would expect very dark, dense rock, unlike the continental rock that we see on Earth. Okay, what about seeing the surface? One of the problems with studying Venus is it has a very thick cloud layer. This same cloud layer, which reflects a lot of sunlight, also participates in the intense greenhouse effect. Makes it impossible to use visible light to see the surface. We can even use infrared light to see the surface. So we've created images of the surface, computer representations of the surface, by bouncing off microwaves using radar. And what we see on the surface, the pictures that you're going to see, are all computer generated. They took the radar data and they used this to create an image of what Venus' surface might look like. For instance, this is a picture of one of the shield volcanoes which is present on the surface. It's actually exaggerated. The elevation here is exaggerated by about 20 times. And you can clearly see this lava flow coming from the top of the volcano. Okay? So again, the geology of Venus is very much like the geology of Hawaii. Lots of shield volcanoes. The crust is fairly rigid on Venus, so again, we don't have any plate tectonics. But again, unlike the Earth, where the crust is constantly moving, and that's why the Hawaiian Islands form a chain, on Venus, wherever you have a hot spot, that volcano is just going to build and build and build. Here's some more shield volcanoes. Here's one right here, another one right here. Here we can see a volcano, and this green line represents the lava flow from it. Again, the higher surface temperatures mean that the lava is going to stay hot for a much longer time. And again, we think that the volcanism on Venus is primarily created by these hot mantle plumes, which take energy from the core, they rise to the surface, they push up on the Venusian crust, melt the Venusian crust, and it's this melted crust which bubbles to the surface. Here's an interesting structure. I just like this one because it demonstrates a few things. First of all, we have what appears to be some type of impact crater. It seemed to punch through the top of the crust and made its way into a magma chamber. And you can clearly see the magma has spilled out since the impact. Again, these are all radar images. These are not real photographs, but they're computer generated from the radar data that we get. Here we see volcanic clusters. All these little points are tiny little clusters. This is sort of similar to what we see on the Earth when we have these small cinder cones. What we don't see on Earth are these strange pancake domes. It's almost like the magma gets close to the surface, but it cools too much to break through, and it just creates this upwarping. Here's some of these pancake domes again. These bubbles will make it close to the surface, push up, and then the magnet is pushed down to create these large depressions. Like the Earth, we see giant calderas. For instance, again, Yellowstone National Park, where Old Faithful is, and you have all those geysers. It really sits at the center of a giant caldera. The same thing is seen on Venus, large circular depressions where magma has built up underneath the surface and then collapsed, producing these large crater-like structures. So again, like many of the other terrestrial planets, Venus has a lot of volcanic activity. It also has highlands and lowlands. In terms of the higher areas on Earth, we know that the continental crust was generated through plate tectonics. Basically, as oceanic crust was recycled, the lighter materials were forced to the surface, generating, initially small bodies that we call cratons, and then these merged together to create protocontinents, and then we had the continents. On Venus, it's a little bit unclear how the highlands formed. I mean, we see highlands on the Moon where we had no plate tectonics. We see highlands on Mars. But the highlands on Mars and the highlands on the Moon were probably created when large impacts created basins or lowlands and created this difference between high and low. On Venus, however, we may have not plate tectonics like we have on Earth, but sort of an analogous system where we have rising mantle plumes and sinking streams. And basically,
As the plumes rise, they upwarp the crust, they stretch the crust, and where it sinks, it probably pulls the crust with it, causing the crust to come together. So there are quite a few plateaus which were clearly not created by mantle plumes, which may be the result of the crust just being bunched up at the locations where the mantle is sinking. So again, it's not true plate tectonics because we don't have the crust broken into plates, but it is at least sort of a tectonic-like activity. And here's some of these different plateaus. The Ishtar Plateau, Aphrodite, Terra, the Phoebe region, the Beta region, the Alpha region, we call them Regios, Thermus. All of these are probably in some way created by some of this downstream. Notice, by the way, this Aphrodite terrain, you can actually see some large calderas on the very outside of this. Now at Ishtar Terra, we have some of the largest mountain ranges on the entire planet. It's the highest elevated and second largest highland region on Venus. And within this are the Maxwell Montes. These are about 11 kilometers above the surface of Venus and are much, much taller than the mountains that we see here on Earth. Again, we don't know the exact mechanisms that built the mountain range. However, they're not volcanoes. They're asymmetric in shape, and it almost indicates that the tectonic activity here, again, not plate tectonics, but tectonic activity, may be some type of fault block mechanism. So again, here's a radar image of the Maxwell Montes. The black lines indicate places where no radar was taken. And here is a area right next to the Maxwell. There's Maxwell right there. This is the Lakshmi Planum. This is a large plateau composed of mainly basaltic lava, which probably pooled due to a large eruption. Yeah, it's strange on the surface. We see a lot of unusual fracture patterns. And again, it's unclear if these fracture patterns are due to thermal contraction or tectonic forces. Now, the Aphrodite Terra is the largest elevated highland in Venus. It's much rougher than Ishtar Terra, but the mountain ranges aren't quite as large. Very complex in terms of its structure. The Ovda Regio is the western part of this. And we do actually see some transform faults there. But again, these aren't transform faults that we see in plate tectonics on Earth. It's just faulting within the overall crust, which is not broken into plates. Here's the Artemis Chasma. It's a large caldera that we saw in the previous images. It's one of the largest calderas on the Aphrodite Terra. And here's the Matmons, the large volcano in Aphrodite. One interesting thing that was discovered is what was thought to be a carbonate lava flow. And this is important because this lava flow that you see was probably produced by something with a very, very low viscosity. If you melt carbonate rock, it has almost no viscosity and runs very, very smoothly. Some speculate that this channel right here was cut by carbonate lava, and this carbonate rock would have indicated that at one time Venus would have had large oceans. Now, in terms of the missions to Venus, there have been quite a few missions to Venus. The earliest missions were Mariner 2. It successfully rendezvoused with the planet, and also confirmed that the temperatures on the surface were very, very hot. So when Mariner 2 arrived, we got our first idea that Venus was not a very nice place. Before the mission, there was speculation that Venus was actually a lot like the Earth, because of the size, but probably just a really hot tropical planet. So, science fiction writers would, imagine a tropical planet with, life similar to Earth, maybe even civilizations on the planet, just, more like the tropics that we see on Earth. Mariner 2 pretty much shut that down. Venera 3 through 6 were landers created by the Soviet Union. They did give some important information about the atmosphere, but none of these made it to the surface to transmit any data. Mariner 5 confirmed earlier atmospheric measurements made by Mariner 2, the Venera probes, and it wasn't until the Soviet Union got to Venera 10 that they're actually able to transmit information from the surface. And Venera 9 was the first to take photos of the surface, and Venera 13, I believe, was the first mission to give us those photos of the basalt rock on the surface in color. Again, all of these probes are very important for studying both the atmosphere and the surface, but some of the best images that we have of the surface came from orbiters which used radar to map. Pioneer Venus, Venera 15 and 16 mapped the surface, but it wasn't until Magellan that we really got a nice high resolution. Magellan operated from 1990 to 1994. In terms of studying Venus today, Venus Express was launched in 2005 and is currently studying the atmosphere. It arrived at the planet in 2006 and was scheduled to look at the planet through 2012, and it still operates today. Now, Venus Express did discover evidence of an ancient ocean and has also confirmed the existence of lightning. Future missions to Venus, the ESA proposed a Venus entry probe. However, I believe that might have been scrapped due to budget problems. And Russia has proposed this Venera D with the primary mission to map the surface at even better resolution than Magellan. So in summary, Venus is the second closest planet to the Sun, very similar in size to the Earth. It has a retrograde spin. It actually spins backwards, okay, and appears to be gravitationally in sync with the Earth in terms of its rotation. Now, of course, when we think of Venus, we think about runaway greenhouse effect, extremely dense, deadly atmosphere. Oftentimes when scientists will warn about the greenhouse effect, they'll say, oh, watch out, the Earth will become like Venus. It'll get so hot that it'll no longer be able to support life. Well, our models don't really support that. The sun really isn't bright enough right now to drive the Earth to an extreme greenhouse effect. But certainly, even a small change in climate, as we saw with Hurricane Sandy, can have devastating effects on on us and on life on Earth. No plate tectonics, however, it does appear there may be tectonic activity driven basically by these mantle plumes. And of course, when we look at the surface of the Earth, it's basically shaped by plate tectonics. On Venus, what's going on in the Earth is really shaped mainly by just straight volcanic eruptions. Venus may have had an ocean at one time. However, that's evaporated and would have been replaced by volcanic eruptions, which have erased, any signs of this past, possible Earth-like conditions. Okay, that concludes today's lecture on Venus, and I will shortly be putting up our lecture on Mars.